Hi, and welcome to Mike Likes Robots, where we share knowledge to accelerate robotics. And I'm continuing this new format of Advent of Code, where I try and complete the puzzle before making the video about it, which means I don't get to show you quite as much of my mistakes and debugging process, but at least I'll be able to do the puzzles within an hour and keep more to a one video per day rate. I'm still trying to catch up to the Advent of Code at the moment. So this is day 18, RAM run, and I've already completed this. I enjoyed it. I found it actually fairly easy, especially compared to some of the previous days. So it doesn't take too long to do. Let me read the puzzle. There are timestamps in the description if you want to skip past. Day 18, RAM run. You and the historians look a lot more pixelated than you remember. You're inside a computer at the North Pole. Just as you're about to check out your surroundings, a program runs up to you. This region of memory isn't safe. The user misunderstood what a push-down automaton is, and the algorithm is pushing whole bytes down on top of us. Run! The algorithm is fast. It's going to cause a byte to fall into your memory space once every nanosecond. Fortunately, you're faster, and by quickly scanning the algorithm, you create a list of which bytes will fall your puzzle inputs, in the order they'll land in your memory space. Your memory space is a two-dimensional grid with coordinates that range from 0 to 70, both horizontally and vertically. However, for the sake of example, suppose you're on a smaller grid with coordinates that range from 0 to 6, and the following list of incoming byte positions. It lists a whole bunch of bytes. Each byte position is given as an XY coordinate, where x is the distance from the left edge of your memory space, and y is the distance from the top edge of your memory space. You and the historians are currently in the top left corner of the memory space at 0, 0, and need to reach the exit in the bottom right corner at 70, 70 in your memory space, but at 6, 6 in this example. You'll need to simulate the falling bytes to plan out where it will be safe to run. For now, simulate just the first few bytes falling into your memory space. As bytes fall into your memory space, they make that coordinate corrupted. Corrupted memory coordinates cannot be entered by you or the historians, so you'll need to plan your route carefully. You also cannot leave the boundaries of the memory space. Your only hope is to reach the exit. In the above example, if you were to draw the memory space after the first 12 bytes have fallen, using dot for safe and hash for corrupted, it would look like this. And it gives an example grid on screen. You can take steps up, down, left, or right. After just 12 bytes have corrupted locations in your memory space, the shortest path from the top left corner to the exit would take 22 steps. Here, marked with O, is one such path. You can see it traces up and around, and then down into the exit. Simulate the first kilobyte, 1024 bytes, falling onto your memory space. Afterward, what is the minimum number of steps needed to reach the exit? You can see I've already given my puzzle answer here. Okay, so this is actually, from the start, you can pretty easily see that there's a grid that you form, after which you try and pathfind from the start to the exit. And that is best done using Dijkstra's algorithm, same as we had on day 16, I want to say. So what I tried to do was try to do it a little bit differently. Instead of using my grid class, I decided to try and use the grid class from the pathfinding crate, which turned out to have a lot of what I wanted. In fact, I had everything that I needed that was in my previous grid and point and directions, while also giving me extra methods that came in handy for this puzzle. So going into the code, you can see we've got the main file, we've got the main function, tests with part A and part B, and here we can see that we're expecting sum 22. And then my part A and part B functions are a little different because I've got the number of bytes that you're expecting to have to simulate. So this was something that tripped me up at first. There's a limited number of these that you actually use to begin with. So in the example, it gives 12 bytes after the first 12 bytes have fallen. So you need to run the simulation after a specific number of bytes have fallen. Now I could hard code the 12 or the 1024, that is here, simulate the first kilobyte, 1024 bytes. But I found it easier to just keep a bytes That is the number of bytes that I'm going to include. So that's part A, and similarly for part B, there's a number of bytes involved. I'll get to that once I get to part B, or part 2. So the first thing to do here is to parse the memory region. So it's fairly simple. All it's really doing is taking all the lines in the puzzle, splitting each line by comma, and then parsing that into 2 integers. Then there's a map which takes the 2 integers and returns a tuple of the 0th and the first integer, and then collects them into a vector. Also collects it into a result containing a vector, and then does the question mark check. So if there's any parse failures, it returns a parse-in error overall. And that's all that's stored inside the memory region. And that's because while doing the puzzle, I found it easier to keep a vector of the points that are going into the grid. I found that easier than by storing the grid of all the cells. And that was so that over time I could add more cells to the grid if I needed to. So the actual part where we use a grid is in the part A, implementation. So what we want to do here is put the cells into the grid as places that we're not allowed to go, and then pathfind from the start to the exit. The grid class from pathfinding made this pretty simple. All I needed to do was take the cells, and then I'm taking a specific number of bytes, hence this copy. So here I'm only taking the first 12 bytes for the test text. Then I create a grid, and this grid has a helper method called fromCoordinates. What that does is take a vector of tuples of x and y coordinates and then gives you back a grid with those coordinates in. Now, that gives me all the places that I can't go in the grid, but that means that the grid only has entries for the places I can't go. In order to pathfind, I need to know all the places that I can go. So at that point, I invert the grid. Now the grid says I have a cell if it's possible to be there, and I don't have a cell if it's not possible to be there. Then I take the end as the grid width versus the grid height, -1, -1. And that is based on the assumption that there will always be one of the points along the right edge and one of the points along the bottom edge. That way I don't need to fix my memory space at 70 square. I just put in all the points and then check what the result is. So from there, we just use dijkstra, again from the pathfinding algorithm. So it starts at 0, 0. It ends at the end coordinate, which we've calculated from the grid width and height. And then the last point is to figure out when I'm at a specific cell in the grid, what points am I allowed to go to? And that's where this neighbors method comes in. So this codes a lot of what I've been doing with the direction, horiz, and vert, and checking whether they're inbounds in the grid or not. It's all handled by the grid class. So now I pass in grid.neighbors with the current cell that I'm in, and then map it to a tuple of that vertex and a cost of 1, because it's 1 cost to move every time. Now, this doesn't work for diagonals. The puzzle explicitly bans diagonals. If it did allow diagonals, I could actually set the grid to have the enable diagonal mode. And what that would do is the neighbors would include the corners as well as the up, down, left, and right. So with that, the shortest gives me an option with the path that it took and the cost that it took, or the number of steps. Then I just take that and I say, if there is something there, give me the cost back. And I return that. So that means that I get an option of the number of steps it takes to reach the exit. So that's all it took for part A. This was pretty simple. The only real thing that tripped me up was putting the wrong number of bytes in to begin with. Initially, I created a grid with all the bytes and then couldn't find an exit and got pretty confused about that. But once I realized that there were a fixed number of bytes you're meant to put in, I then included that in the arguments, and then it solved very quickly and pretty simply. So that gave the answer of 304, and then it brought me on to part 2. The historians aren't as used to moving around in this pixelated universe as you are. You're afraid they're not going to be fast enough to make it to the exit before the path is completely blocked. To determine how fast everyone needs to go, you need to determine the first byte that will cut off the path to the exit. In the above example, after the byte at 1, 1 falls, there is still a path to the exit. However, after adding the very next byte at 6.1, there is no longer a path to the exit. You can see it's been blocked off here. So in this example, the coordinates of the first byte that prevents the exit from being reachable are 6.1. Simulate more of the bytes that are about to corrupt your memory space. What are the coordinates of the first byte that will prevent the exit from being reachable from your starting position? Provide the answer as 2 integers separated by a comma with no other characters. You can see here my puzzle answer was 50, 28. And I'll show you how I got to that as well. So the first thing is that because we know from part 1 that in the test text we can skip the first 12, and in the real input you can skip the first 1024, part A wouldn't have been possible if there wasn't a path, a valid path at that point. So we can skip those to try and save ourselves a bit of computation. So that's what the skip bytes is. So what this algorithm does is it's pretty naive. It basically just iterates from that point to the end of the all cells that I've taken from the input. For each one, it removes it from the grid. Remember, the grid contains valid positions. So it removes the vertex from the grid and then recalculates the Dijkstra's algorithm. And as long as that gives something back, it has some valid result, then part B will give the answer. So it does all cells.iter, it skips skip bytes, and it finds the pair of coordinates x, where if you remove it from the vertex, remove it from the grid, and then calculate Dijkstra, the result is none. Then that find gives you that x coordinate back, and then I have to use the .copied method because the find takes references to the coordinates rather than the actual coordinates, and I want to return the actual coordinates. So that's all that's doing. It's copied will create a copy of it, which means that I can keep a pair of U sizes. The one thing that tripped me up here was by not doing the skip bytes correctly. So what I initially did was I skipped skip bytes in the all cells.iter, but I forgot to remove them from the grid at first. So here I fill the grid in instead of putting in all the cells and then inverting it. I simply fill it with valid positions, and then for the number of skip bytes I put in, I remove those vertices, which is another way of doing from coordinates invert. In fact, it's I think identical, so I could have easily done it either way. Looks like I'm getting a compilation error, something I've changed between runs. No, it seems to work just fine. It ran, so I don't know why it's giving me an error there. So the first time when I did the skip bytes incorrectly, it gave me the wrong coordinates. It gave me 6232. Then I went back and realized that the skip bytes was done incorrectly. I removed those vertices, and then I correctly started using the algorithm, which gave me the final answer of 5028. And you can see just then that it did take a little while to calculate. I can run it in release mode to make it slightly quicker. Well, actually, that time was pretty quick. So there is probably a more optimal way of doing this, but I think this works perfectly quickly for me. I got the correct answer, and I did it without too much difficulty. So with that, that is day 18 complete. Thank you for watching, and I'll see you in the next video for day 19.